Hey there, welcome to another lesson in Mr. Coulter's classroom, Unit 1, Lesson 15, adding the angles in a triangle. This lesson, to be very honest with you, has been kind of difficult to figure out how to present because it's such an interactive lesson, and I really hope that I give it justice with the tasks that I try to complete and the things that I try to do. So bear with me as we get going. I do want to apologize for the piece that or the page that I have here and the way that it's printed. I hope that you'll be able to fill in your information appropriately and easily enough. So what we're going to do today, the goal today is to have a greater understanding of how every single triangle is related to each other. To begin with that understanding, I think it's important that we recognize what kind of triangles that there are and what those triangles look like. So as we get going, you're going to have some questions to answer and some feedback to give, and let's see how you do. So rather than using this table right here, we're supposed to complete the table by drawing a triangle in each cell that has the properties listed for the column or for its column and row. If you think you cannot draw the triangle with those properties, write impossible in the cell, and you're going to share your drawings with a partner. And you see with this piece, it's talking about partnerships, and under the circumstances, we can't do that. If you disagree with each other, then reach an agreement. Because these spaces are so small, I apologize. That's how they printed out, and I'll have to see if I can make sure to format the right way in the future. But I'm going to go ahead and use a larger scale model that I made to make sure that we can understand this. So very first thing, tell me what you think a scalene triangle is. Here we go with the scalene triangle. We're supposed to draw an acute scalene triangle. We see that a scalene triangle has the side lengths are all different. So I'm going to go ahead and use my triangle and some straight edges just to make sure that I get, an acute angle. So we have to make sure all the angles are less than 90 degrees. But all the side lengths have to be of a different length. So I have to be really careful to not go too far. Let's make sure that that is not going to be 90 degrees. Good. And we'll say that each of these side lengths, just to make sure that we understand, we'll call this one like, I kind of look at that one. It looks like that's about 12 millimeters. And that one, oh, good, it's only 11. So this one's 11 millimeters. This one's 12 millimeters. And this one right here is 9 millimeters. All different lengths, okay? When we talk about a right scalene triangle, that one's a little bit easier to draw. I'm going to actually use the right angle edge of my triangle here. Make sure that both of my sides are different lengths, that the length of my hypotenuse is going to be longer than the other two sides. It will for sure be that. Don't forget to add the right angle. And how do I know that they're different lengths? Well, we can measure and we can see that this one is about 13 millimeters. Actually, I'm going to change this. Let's do centimeters on this one. That's going to be 1 3/10 centimeters. Across the bottom, we're looking at 3.5 centimeters. And my hypotenuse will be just slightly longer. Is going to be 3 8/10 centimeters. Now, what about that obtuse? Now, this one hopefully will be kind of easy to draw. We'll go ahead and make this side long and this side long, remembering that this angle right here has to be greater than 90 degrees. And with this side over here, we can see that all three side lengths on there are definitely longer. Right, so there is a scalene triangle. All the sides are of a different length, acute, right, and obtuse. Go ahead and give it a try. Make sure you're drawing those angle triangles in there, but make sure you draw your own. Right? If you need to copy mine, that's totally fine as well. Next one, what is an isosceles triangle? Go ahead and answer the question. All right, welcome back. An isosceles triangle we know has at least two sides that are equal in their length. So when we talk about an acute triangle, we can talk about, we can't use that as a 90-degree angle, but I can certainly use this one. I know this edge is 45 degrees, and I know this edge is 45 degrees. So as I draw this, I want to go ahead and be careful with this to make sure that my side lengths are exactly the same length. So I'm going to go ahead and just get started with that to know that I have an angle that's going to be 2 centimeters long here, and I'm going to make sure this side is 2 centimeters long as well. And I see that this one is also 2 centimeters. And now I just have to make sure that the third side is not 2 centimeters. I see that it's actually 1 7/10 centimeters. So this is great. And it's also an acute triangle. Can I draw a right triangle that's isosceles? Well, absolutely. In this case, I'm going to go ahead and draw this one. Most common, we're going to see isosceles triangles that come together, like this. We'll go ahead and draw this one with 2 centimeters as well, just to get started right there. We'll get this 2 centimeters long. But we can see that this is a right angle because I used a right angle. So here's the 90-degree angle. And then the straight line across the bottom, 2 centimeters on the side, 2 centimeters on the side. The hypotenuse must be longer in a right triangle than both of the side lengths, and this is a 3 centimeters approximately in its length. Obtuse, this one's kind of fun because I can just make it whatever I want. Let's make these sides a little longer. But what do we have to remember? 3 centimeters on this side, and if we're talking about isosceles, these sides have to be equal in measure. We just want to make sure this is longer, or excuse me, opened up more than 90 degrees. 3 centimeters on this side. And then, of course, across the bottom, let's see how long that is from there to there. Looks like 5 3/10 centimeters. Awesome. Equilateral triangle. We know that under an equilateral triangle, there is only one equilateral triangle, and that's where each of the angle measures are 60 degrees. So when we draw this, we need to be able to draw this triangle. You're going to have to bear with me. But all of the side lengths, equilateral triangle, all of the side lengths, let's see how close I am. There's 1 7/10, almost 1 7/10. Oh, 1 8/10. So if I'd make sure, let me measure this again. 1 7/10. So maybe I need to open this up just a little bit more to make that 1 8/10. That was pretty good. And 1 8/10. I know this is an equilateral triangle because all 3 sides are 1 8/10 units long. But the consequence of that, of each of the 3 sides, is each of these angles inside will also be equal in their measure. The hardest part with this is the question on this equilateral triangle is, can that be drawn as a right triangle? If I've said each time that this hypotenuse, this side over here across from the right angle, is the longest side, and if that's the case, under a longest side, to have a right equilateral triangle is actually impossible. And if we think about an obtuse triangle, when we see that piece, when they open wide up, this side is clearly much larger than the other two, and to be greater than 90 degrees, if it wasn't possible with a 90-degree opening, then it's certainly not going to be possible with an obtuse angle. So that one's also impossible. Just a quick brief on triangles. Now we're going to get to the 8th grade part of triangles. You'll also see this in 7th grade. What's going to happen here is we're going to learn that every single triangle actually has a relationship. So this is one of the other parts to this lesson, is that you would be given a card with pictures of a triangle on it, something like this. And then the measurement of one of those angles is labeled, like on this one. This angle right here is 40 degrees. And you're supposed to measure 2 of the other angles. So I want you to go ahead and make a prediction. What do you believe these other 2 angles are? Okay. And then you would take that around and try and find other students that help you to put together what those other measures are, and you would enter the 3 angle measures for your triangle on the table and your teacher's posted. So I would have that up on the board. In this case, I would normally do this on a shared doc, but we're not going to be able to do that. So what I'd like for you to do is take a look at the ones that I'm going to present. So here's one of the cards. The one that I showed you is a 40-degree triangle, or 40-degree angle here in this triangle. And then if I go and wander around and try and find other kids, I may see one that looks like this. And I would know, well, are those triangles equal in their measures? No, these triangles cannot be congruent because they're not equal in their measure. And I would continue to wander around, and maybe I'd find another student that has another card that looks like this one. And I would have to say, are these triangles equal in their measures? And I could see, no, they are not the same triangle. So this one is not congruent either. And I would continue to search until I find another student that has another triangle that looks like mine. Wow. And I see that these ones, they certainly do look like they're similar triangles or even equal triangles. And so I would actually want to probably set this up and see, are these triangles equal in measure? And by overlapping, I know it's hard to see on the video, but I can see in an overlapping fashion that this triangle matches this triangle exactly. And so I know that these two triangles are congruent. I would continue to search until I found the third person out there. And I would say, is this also congruent to my triangle? And I kind of look around and I'd see, and then I have to think, oh, wow, well, maybe this is a reflection of this triangle and a rotation. I'm going to go ahead and sketch this one so you can see it on the reflected image. And then that reflected image, we see that the smallest angle down here is 20 degrees. Reflected on there is 20 degrees. And then I look at the three angles together and I see that these three triangles appear to be congruent. So then I need to be able to look at these three triangles and say, well, what are the measures for the triangles that we would post? I see that this one is 40 degrees, 120 degrees, and 20 degrees for the third angle. And on that post, we would say, we would call this maybe the measure M of angle 1 is 40 degrees, measure of angle 2 is 120 degrees, and the measure of angle 3 is 20 degrees. And then we would see all these on that chart, and then we would see all the relationships between all of them. We would see a pair of these ones right here that would end up being 40, 80, and 60 degrees. And then we would even see another pair that would look like this. And we would see, well, oh, that one's a 90 degree, and then a 40 degree, and then a 50 degree. And then we would have discussion and say, well, what do you notice about each of these three triangles? Take a moment and tell me what you notice about each of these three triangles in this table that we created. Okay. Hopefully what you gather from that is that if I look at each of these three triangles, let's go ahead and remember what the lesson title is. It says adding the angles in a triangle. So let's see what happens when we add up the angles in the triangle. We see the measure of angle 1 plus the measure of angle 2 is 160 degrees plus 20 more degrees. It's 180 degrees. We're going to call this the interior angle sum. We do the next one. 40 plus 80 is 120. 120 plus 60 is also 180 degrees. 90 plus 40, wait a minute, 40 and 50 is 90, so 90 plus 90 is 180 degrees. And I see that three different triangles all have the same interior angle measurements. Now, why does that really matter? What this begins to prove is a common rule, not a common rule, a law in mathematics, that all triangles, when speaking of their interior angles, have a sum of 180 degrees. So that's all great and well, but what happens if I'm given a triangle that doesn't have any measurements, such as this one? How could I go about proving that this triangle has the same thing going on, that these three angles add up to 180 degrees? Take a moment, go ahead and write down a thought or a process, what you think you could do, and then join right back with me. All right, in the lesson it says your teacher would give you a piece of paper with 3 sets of angles in a blank space. I want to go about this a little bit differently because of the way that it relates to the lesson summary. What we're going to do with this triangle is, the goal with this is to be able to prove that these 3 angles, let's look at this. I'm going to call this one the measure angle 1. I'll call this one angle 2. and I'll call this one angle 3. So the question is, how could I get these 3 angles? How would I take this triangle and prove that angle 1, the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 actually equals 180 degrees? Still stumped? Grab a piece of paper and cut out a triangle and see if you can figure it out. If you're still here and you didn't grab that piece of paper, yes, I am going to show you. So let's see here. If I take, let's just take these interior angles. Now let's go ahead and we're gonna rip these off of here. That way I can play with them. And then I take these 3 angles, and I know that they were once part of a triangle, right? So how could I verify that these 3 angles, angles 1, angle 2, and angle 3, add together to equal 180 degrees? Still waiting for me to tell you what to do, huh? Well, we know some other things about 180 degrees. We know that 180 degrees also creates a straight line when we're working with a straight angle. So here's a nice straight line right here. Let's call this a straight angle. We're going to call this right here, I'm going to make this point Q. And on point Q, what I know about 180 degree angles is that everything that goes from here to here is 180 degrees. So by that logic, what if I took my angles, angle 1, and I added angle 2 to the angle, and then I took angle 3, is it going to fit? Take angle 3 and I slide that in there, and I recognize when I add these 3 angles together, take a look at what this makes. Taking what used to be a triangle and those interior angles and adding them together created what we call a straight angle. That straight angle is 180 degrees because it's made up in this case of multiple rays. Usually what we're going to see with straight angles is just 2 rays that go out this way, but when we talk a straight angle, we're talking it can be actually any number of angles that are added together to equal 180 degrees. The important piece is that we recognize that this angle along the bottom is 180 degrees, and these 3 angles added together makes that 180 degrees. When we experiment with these angles in a triangle, we can find that the sum of these measures is equal to 180 degrees, and that's the same exact thing as this straight angle as it is with any of the interior angles of the ones we saw earlier. And that's the lesson. Understanding this concept will allow us to use rigid transformation with all of the angle relationships you were studying over the last couple days, vertical angles, alternate interior angles, complementary angles, supplementary angles. We're going to be using those to prove angle relationships on a little bit more complex graphs, but I don't want to show those to you yet. Instead, what I want to show you is your lesson summary, because we're at the end. Anytime we see a 180 degree angle such as this, we call that a straight angle because it's made up with 2 rays, they point in opposite directions, and they form a straight line. We know that we can actually add up other angles to make up a straight line. If we experiment with those angles inside the triangle, we find that when we add those 3 angles together, it creates an angle of 180 degrees, a straight angle, which was the same thing as adding up the 3 angles inside of the triangle. That experimentation, when we look at these pieces and we look at this as angle 1, angle 2, and angle 3, when we add those 3 angles in here, we saw that that was angle 1 here, angle 2 here, and angle 3 here. So we make that connection between the interior angles of a triangle being added together to make a straight line. So make sure to go back through these. If we physically cut them off of the triangle, and line them up on a single vertex, we find that they make a straight line or a straight angle. The major goal of today's lesson is not to say triangles equal 180 degrees. That's a no-no, right? I could try and say that. No, triangles equal 180 degrees. And that would be a no. Please don't say that. Please don't get that. What I need you to understand is that the angle sum, that's SUM, addition of any interior angles. Oh, I don't like the way this is turning out. I would actually want you to notice that the interior angle sum, that's better. The interior angle sum of any triangle is 180 degrees, meaning that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180 degrees. There's the big idea of the lesson. All triangles are like this. We're going to use this over the next couple lessons. Thanks for hanging around today. Thanks for making your conjectures. I hope that today was a great lesson for you. And thank you for not ever giving up, even when things get hard. Have a great day today.